Hi, this is my Lab 5 presentation. So in this lab, we test the interactions between a magnet and an aluminum tube by dropping a bar magnet through a roll of aluminum foil. We then measure the time it takes for the magnet to get through the tube. This may seem like a very simple procedure, but it produces very interesting results based on complex physical principles. So the fundamental physics principles involved in this lab are, mainly, Faraday's law, which states that a magnetic flux changing with time actually creates curly electric fields, which in turn can form an EMF if there's a closed path. Other important ideas are Lenz's law, which states that the magnetic field produced by an induced current opposes the change in flux within the ring. The important formula that the current I equals the EMF over R, the Biot-Savart law to help us calculate magnetic fields, and Newton's second law. To add some context to my experiment, here are some important values determined before the trials. The tube of aluminum foil is 0.31 meters long, and the aluminum foil is half a centimeter thick all around. As for the bar magnet, it is 0.024 kilograms and has a magnetic dipole moment of 2.05 amperes times meters squared. Here's a quick video to help demonstrate the lab. As you can see, I dropped the magnet through the tube of aluminum foil, and after some delay, it finally drops out of the other side. I did this procedure 6 times and used a video scrubbing tool to measure the time it took for the magnet to fall through the tube for each trial. Here are the results. In each trial, the magnet took between 1 second and 1.5 seconds to get through the tube, with an average time of 1.2 seconds. If you were thinking that this seems like a long time for something to fall 31 centimeters, you're right. The magnet takes much longer to fall through the tube than it would have in free fall, by almost a whole second difference. Why does this happen? When the magnet falls, the flux at any ring in the tube is changing, and this causes curly electric fields due to Faraday's law. In turn, this forms an EMF and an induced current around the aluminum foil loop. Due to Lenz's law, we know that the magnetic field formed by this induced current opposes the change in flux, and in doing so, applies an upward force on the falling bar magnet. With this upward force opposing the downward force due to gravity, the magnet takes longer than normal to fall through the tube. So now we move on to the coding portion of the lab, where we try to model this experiment. The first steps of the code are to define some constants and make the tube and magnet objects. Next, we define a function to calculate the magnet's magnetic field at a given location, and another function to calculate the derivative of the flux with respect to time, d flux dt, given a ring in the tube. Next, the code enters a loop that simulates the magnet object moving through the tube. In this loop, it calculates the force due to gravity on the magnet. It then enters another loop which iterates through every thin ring in the aluminum tube. Within this loop, it calculates d flux dt at each ring, and then uses this to calculate the induced current in the ring. It then gives the ring a color based on the current's direction. Finally, the code calculates the magnetic field of the bar magnet at the position of the ring, and eventually the upward force exerted on the magnet by the current. It then calculates the net force on the magnet and updates the magnet's velocity and position before the outer loop repeats. When the program is run, the blue ring shown travels down the tube, and this velocity over time graph is created. Notice that the magnet accelerates when it's dropped, then reaches a constant velocity for the bulk of its time in the tube as the upward magnetic force on the magnet cancels out the gravitational force. The program estimates that it would take my magnet 1.384 seconds to fall through my aluminum tube, which is very close to the actual results in my trials. So now to the lab questions. What if the resistivity of the conductor were reduced as close as possible to zero? As shown by the equation, I equal EMF over R, if the resistance approached zero, the current would become very large, so the magnet would fall quite slowly. Now, what if holes or slots were cut into the tube? Then the current wouldn't be able to close correctly, so the ring currents would be much smaller and the upward force on the magnet would be smaller. Thus, the magnet would fall through the tube faster. This lab was very interesting because it was such a simple task of dropping a magnet through a tube of aluminum foil, but due to the complex relationships between magnetic fields and electric fields, the experiment produced interesting and quite cool results. Thanks for watching!